What's going on, guys? Hope the lectures have been going well so far. In this video, we're going to be looking at some very important precursors to solving the information problem using electricity and circuits. Now, to do that, we're going to take a deep dive into two main things. First, we're going to look at transistors. We're going to learn about what they are and what role they play in electrical circuits. Now, this is important because transistors were the forefront of the revolution that happened in Silicon Valley. Then we'll see how we can actually combine transistors in really intelligent ways to create logic gates. Now, what logic gates do is they enable us to perform logical operations using electrical circuits. Now, to see how all that stuff gets done, let's just get straight into the presentation. Alright, so if we have a look at the information problem, we know that the core of it can be solved if we're able to create information, store information, retrieve information, edit information, and delete information. So then the real question that we want to ask ourselves is, how do we do all these things related to the information problem via a circuit? Well, we're going to start building a circuit of our own to show you how it's done. Now, in the circuits of the previous videos, we've already seen how we've got the wires, we've got batteries, we've got our light bulbs, our switches, and so on. I'm going to introduce you now to a new part that we're going to later add to these circuits. Now, to build this part, we need to start with something quite important, and that's the silicon semiconductor. This is just a wafer or slab of pure crystalline silicon. A wafer just being that flat rectangular shape that you see, and crystalline just means the way that the atoms are arranged in there. But what matters is that this is pure silicon. Now, pure silicon is a semiconductor, which means that it's conductive only under certain conditions. So in its pure form like this, it actually doesn't conduct electricity, but when you heat it up, you can turn this wafer into a conductive material, like a piece of gold or copper. Now, as we're about to see, this is a precursor to the transistor. And the transistor is the most important piece in our electrical circuit puzzle. And so fittingly, Silicon Valley, the birthplace of the computer revolution, gets its name from the silicon semiconductor. Now, this piece of pure silicon is somewhat interesting, but it's not that interesting. We can make things more interesting to this wafer of silicon if we do something called doping. Doping a silicon semiconductor is simply introducing impurities, or compounds that are not silicon, into the structure itself. The concept of doping isn't restricted to silicon or anything else. You can introduce impurities into any sort of substance you like. But we discovered that if you dope a silicon wafer in interesting ways, you can give it some really cool properties. So if we look here, if we dope the left side of the silicon wafer with phosphorus, the middle portion with boron, and the right side with phosphorus again, we give this crystal some very, very interesting properties. Now, the most detail I think we need to go into why phosphorus and boron, for example, is that phosphorus is part of the fifth column of the periodic table, so it's missing 3 electrons in its outer shell, and boron, being in the third column of the periodic table, is missing 5 electrons in its outer shell. Now, we're about to see the impact of what that does. But from a high-level perspective, we don't really need to worry too much more about that. So in this situation, what we end up creating is a new type of semiconductor with interesting properties. Now, if we look at the 3 regions that we doped, if we checked out the region that we've doped with boron, we can see in the atomic structure that we have 1 boron atom surrounded by 8 silicon atoms. Now, given boron is in the third group of the periodic table, all we really need to know is that this arrangement means that there is an extra spot for an electron that is not met. And we call this a hole. A hole means that there's an empty space that is not occupied by an electron. And if we were to add an electron into this structure, it would have a strong desire to occupy that space. And so we call this blue portion of the doped semiconductor that has these properties the p-type semiconductor. I'm just going to say, don't worry at all about what that p-type means or why we call it. So now if we take a look at the portions of the semiconductor that's doped with phosphorus, we can see that its atomic structure has one phosphorus atom surrounded by 8 silicon atoms. Now, phosphorus, having had 5 electrons in its outer shell, shares 4 of them with the neighboring silicon atom, and so has 1 electron roaming around freely, kind of like a lost soul. And so this brown portion of the doped semiconductor is called an N-type semiconductor. And so if we have a silicon semiconductor doped in the following manner, we have created a transistor. Specifically in this case, we've created an NPN transistor. Now, there are multiple types of other transistors that are doped in different ways, but at the end of the day, they all perform and behave in the same way. And so what we've ended up with is a wafer of doped silicon that has an P-type semiconductor in the middle with a bunch of holes and spaces for electrons to flow into, surrounded by 2 N-type semiconductors that have extra electrons that are roaming around looking for places to go. And that's what a transistor is. Alright, so now let's understand the workings of a transistor. So if we look at the circuit, we see that it's the exact same setup as in the last video, except in place of the switch, we now have our transistor there. So in this setup, we see that the light bulb is off, so let's see what's going on. First, let's enrich this diagram a little bit. So let's draw the electrons that are in the N parts of the transistor, so in the yellow portions. We also want to show the direction the current is going in if the light bulb would have been on. And we also have the holes or the empty spots for electrons that's in the blue part of the transistor. So we may expect in this scenario, because of the force of the battery, the electrons that are roaming around on the left yellow part of the transistor should be able to jump into those empty holes in the blue part of the transistor, and then again jump into the yellow part on the right side of the transistor where other electrons are just roaming around, and then go along down in the circuit, down through the wire and back into the battery. But that's not happening, so what's going on? Well, right now, if an electron were to make that initial jump into a hole in the blue portion of the transistor, just like when you get out of your spot to occupy another seat, you've now left that spot that you were initially in open. So right now, due to the force of the battery, only the electrons that were in that junction would be making that jump. So when that happens, you're just creating a bunch of open spots on the yellow part of the transistor now. And so no matter where the electrons jump, there will always be some kind of a barrier of empty spots within this transistor that prevents electricity from going through. Okay, so this situation isn't that useful to us. So let's go ahead and add another circuit into this diagram. So we've just added a new wire coming out of the blue part of our transistor, going into another power supply. Then we have a switch, and then this entire circuit is connected into the wire that goes back into the left portion of our transistor. So now if we were to draw the electron flow of our circuit, we still have the same electrons flowing in our original circuit like before. And now for the additional circuit, we have the electrons flowing in this direction, which you can see also from how the battery is connected in that circuit. So what we have here now with this wire coming out of the blue part of the transistor, we now give the option to electrons that jump into this blue part of the transistor to either go up and into the wire that's in the new circuit that we added, or alternatively jump into the right side of the transistor and continue down along the circuit. And what that extra wire does basically is it means we can continually keep taking electrons from out of that middle part of the transistor. And so we'll now have a desire to keep replenishing that middle part of the transistor with new electrons. And as a result, when we close the switch, the barrier disappears and electrons can take either one of those options, and so electricity flows through both circuits. And so our light bulb turns on too. And therefore, we can say that the state of our original bit, our original wire here that's circled, is fully dependent on the state of the second bit. Electricity in the first bit will only flow if electricity in the second bit is flowing too. So I'm going to call our second bit, this one over here, the state of I, or the state of the input. And I'm going to say that it determines the state of the output, the state of the big wire. And so this is how you can control electricity in one bit with electricity in another bit with no moving parts. Right here I'm talking about the transistor being the point of control that has no moving parts. Of course we still have the switch there, which is a moving part, but it is not the location of control that determines the state of the output bit. Really, we want to have these switches here so that we can feel like we're the ones in control of this output bit because we're in control of the input bit, using our hands to move the switch up and down. Eventually though, we are going to reach a point where we have no more switches in our computer, and the entire computer is controlled by electricity and transistors all on their own. Alright, now that we know how transistors work, let's see how we can leverage transistors to create logic within a circuit. In this context, what we mean by logic is the same kind of logic that we apply in our daily lives. For example, if I'm filming this video right now in my room is in my apartment building, then you can say that I'm filming this video in my apartment building. So here, logic refers to looking at a set of inputs, in this case, me filming a video in my room and my room being in my apartment building, and determining or stating an output based on that. In this case, me saying that I'm making this video in my apartment building. And so what it comes down to in the end is that the output or the statement that I made can be consistently determined and validated based on the initial set of inputs or conditions. Here, the inputs refer to the state of two specific bits. So two specific wires, each of which can have electricity flowing through it or not. And the output also refers to another designated wire that can also have electricity flowing through it or not. And so when we're talking about a circuit being able to perform logical operations, we're saying we're giving us the ability to determine the state of the output bit based on the state of the two input bits. I think we're going to be able to understand this really well once we get into drawing the circuit itself. So this is the first logic gate that I want to look at. It just looks like a regular circuit, but that's exactly what logic gates are. So you have current in our output bit that's flowing in this direction. Each of the additional loops of wires coming out of the two transistors has a switch. So I'm going to call this one input 1 and the other one input 2. These are going to be the inputs of our logic gate. And we also have our light bulb giving us the state of the output bit. And so both of these input bits have some kind of control over the state of the output bit. So to get a good idea of what's going on here, I'm just going to move my circuit down here, give me more space. I'm just going to draw a table to list all the different combinations I can have of the states of inputs 1 and 2, as well as the output that I should be expecting. So if we look at this first situation now, if both input 1 and input 2 are off, so the switch is being open, and the state's therefore at 0, it's pretty straightforward from what we just saw that electricity is not going to make it past that first transistor, and so the output bit is going to be off, so that light bulb is also going to be off, and we give our output state of 0. Alright, say now I only turn on the first input. Now first bit is going to be allowing electricity to flow through the transistor. However, it's still going to get blocked at the second transistor because our second input is off. So electricity stops there. Now if I flip these switches and so turn input 2 on and input 1 is off, well, we still kind of have the same scenario as in the first case where electricity is not going to make it past the first transistor because input 1 is off. And so that barrier forms in the first transistor and we stop there. So the state of the output bit is also off. So we give that a value of 0. And now if we close both switches, so inputs 1 and inputs 2 are both on, that means electricity is going to be able to go through the first transistor as well as the second transistor, and therefore complete this circuit for the big wire. And therefore our output bit is on, and so the light bulb also turns on. So this kind of a circuit packaged as a logic gate has a specific name, and that's an AND gate. And it's called an AND gate because the output bit will only be on if both of its input bits are on too. If either one of the input bits are off, then the output bit will also be off. And that's how you're able to make the output bit behave the way that you want it to given a set of conditions. So before we move on, there are just two things that I want to go over here. So firstly, this table here on the left has a name, and that's a truth table. That's just the name that we give to this kind of table that denotes the logical output that you should be expecting for a series of inputs. And secondly, and more importantly, this circuit diagram is getting a little bit busy if you ask me. We got a lot of batteries going on, we got our inputs, connected into the circuit in a unintuitive way. The output bit is like this whole wire that's going throughout the circuit, kind of connected also to the input bits and so on. So I think what we can do is we can simplify this diagram and actually start putting this type of a logic gate onto a computer chip. And honestly, when it comes to being an empowered software engineer or programmer, you don't need to know about transistors and circuitry beyond this point. Going deeper into how we actually implement these things inside computer chips starts to go towards the electrical engineering, electronic engineer branch. And that's not what a software engineer or programmer does. A software engineer leverages these circuits to be able to use them to solve problems that have to do with information. And that's why I stress that learning about this is quite important, because when you're going to actually write code, this is actually what you're going to be doing to solve these problems. Cool, so let's simplify things now. Start making our computer chip and actually build our diagram as part of being on that chip. So we first make our green plastic board that's in the shape of a square. It's just like a plastic scaffolding that holds things together. You've seen most of these chips on Google Images and whatnot. They all have these green plastic scaffoldings, so we're going to use green. Then now coming out of the left side of this scaffolding, let's draw a wire and also another one. So these wires are the two input bits. So we'll add a switch to each of them too. These are the exact same two input bits as inputs 1 and 2 in the diagram above. So now both these wires are going to enter the AND gate. So this half circular shape here that I'm drawing. And then we have the output wire coming out of the AND gate and then going back into the chip. And so here are the rules for the chip system to better make that relationship between the two diagrams. The whole circuit still exists in this chip system, but it's kind of embedded and hidden here under many parts. So firstly, the power supply, so the different batteries that you saw, those are inside, you can think of those as being inside the green chip somewhere. So the wires that are coming out of the left side of the chip are still connected to a power source. And the output wire as well that goes into the chip is also connected to the circuit. But all this is hidden in the green chip somewhere. You can think of it as just now, instead of 3 batteries, it's a kind of shared power source that lives throughout the inside of that green chip that we're not going to see, and we don't really need to see this. Then inside the logic gate here, so I'm just going to color this in brown. Just imagine this is where the transistors are. This is where the point of control for this circuit is made for this AND gate. And we've hidden all of this again inside that logic gate symbol. So that half circle, which is the symbol for an AND gate, all the transistors are hidden inside there. And so yeah, there's still no moving parts inside this AND gate, as you can imagine. You can also think of this AND gate having some kind of additional connection to the board underneath where the power connects to these transistors. But that's about it. We've simplified our logic gate and we've put it on a computer chip. Now we're able to just focus on the inputs coming from the left, going through that logic gate, and the output leaving that logic gate and going into the chip. Then we have our switches, again, still to turn on and off the states of our inputs, and then our output will act accordingly. In this case, turn on when only both inputs are on. However, we're not going to need the light bulb anymore. I think we get the point, and there are no light bulbs in computer chips, so we don't need that anymore. But there you have it. This is an AND gate as expressed in a computer chip. And this is the foundation we're going to build off of to finally build the rest of our computer. So before we finish up this lecture, I just want to stress that a logic gate can carry out any type of logical operation that you want. It just depends on what kind of behavior that you want and how you set up the circuit to reflect that. So let's quickly check out these two additional logic gate types and see what their circuits are doing, and then try and complete the truth tables for both of them. So starting up here with the OR gate, from the name of it, you can pretty much guess what it does. Basically, the output of the OR gate will be on if at least one of its inputs is on. So either one input or the other input or both inputs being on will turn on the output as a result. So checking out the first situation right now with both input bits off, so the switch is open, we see that electricity coming out of the bottom battery reaches the junction and then can go through either the transistor from input 1 or the transistor from input 2. However, since both inputs 1 and 2 are off, then they stop there, and so the output bit is off. Okay, say now we turn on input 1, so close the switch on input 1. Now electricity coming from our output battery, once it gets to the junction, is able to get through the first transistor, so continues flowing down and then goes through the output bit, and so we have a completed circuit, and so our output is 1. Flipping the switches now in our third case with only input 2 on, again, electricity is going to be able to flow through now the second transistor, and the output bit turns on as well. And now finally, with both inputs on, electricity is able to go through both of the transistors, and so our output bit also turns on. Cool, and so that's the workings of an OR gate. And on the right here, you see how an OR gate would look like when put on a chip. It's the same thing as our AND gate, except the symbol is different. It's kind of like a stretched half-moon spaceship looking thing. So that's an OR gate. Now let's move on to the NAND gate quickly. Now if you take a look at the NAND gate circuit here, just the one thing that we've added that's new is a resistor up there. We'll see why the resistor is there. It's tied to the hint that's below the diagram. So one other thing to note about electricity is that it likes to follow the path of least resistance to get to its destination. So when met at a junction like this, if one wire has a resistor and one other wire does not have the resistor, electricity will want to take the one that doesn't have the resistor. So let's look at the first case with both of our inputs off. What you can tell is that once we reach that junction, electricity is not going to make it past the first transistor, so the only option it has is to go through the resistor and through the light bulb, so the light bulb will turn on and our output is on. Now, same thing if we turn on the first input. Once electricity reaches the first transistor, it's going to be able to get through. However, it's going to stop at that second transistor, so yet again, the only option it has is to go through the resistor and the light bulb wire, so the output is on again. Then we flip the switches, so now input 2 being on and input 1 being off. We get the same scenario. Electricity is not going to be able to go through the transistors because the first transistor is going to be blocking the electricity, so yet again, we only go through the resistor and the light bulb again, so our output is on. And then finally now with both inputs on, therefore the transistor barriers have been eliminated for both those transistors. So now electricity has the option to go through either of those junctions. Now if the resistance between both of those wires, so wire 1, the output wire, or the wire with all the transistors, if the resistance is the same for both of those wires or for both of those paths, then electricity will kind of go halfway between the two, so it'll take both paths. However, with the resistor up here, we've added some extra strong resistance, meaning the path through the transistors is actually much more smooth and much easier to go through. So electricity is only going to take the path through the transistors, completely ignore the path through the light bulb, and so therefore our output is off. And so when both inputs are on, our output is off. And that's the working of a NAND gate. It basically is the opposite of an AND gate. In this case, the output is only off when both inputs are on. And so on the right here, we have what a NAND gate will look like on a chip, on our chips. It's again, we have the two inputs coming into the logic gate, and then we have the symbol here of a NAND gate, which is basically an AND gate, that half moon circle with an additional smaller circle coming out of it. And then we have the output bit going back into the chip. Cool, so that's it for this lecture about logic gates. Here is a nice diagram showing you all the different other kinds of logic gates that also exist in electrical circuits. So we went through the AND gate, the OR gate, and the NAND gate. But there are other types of gates too, right? There's a NOT gate, which reverses the outputs based on the input. Then we also have the NOR exclusive OR and exclusive NOR gate. We don't need to look at how these things work pretty much. Just there are the truth tables under there for you. But yeah, that's pretty much how we're able to implement logical operations using electrical circuits. And then we've seen how we can adapt them and start putting these logic gates onto our computer chip. And now we are fully ready to solve the core of the information problem using electrical circuits on our computer chip, which goes over to the next lecture, where we're going to finally build what makes up fully half of what we call a computer, and that's random access memory.